Hi everyone. In this video we're going to go over the classical open loop tuning methods, Conankun and Conan Marlin, using the Control Station LoopPro Trainer software and specifically the furnace air-fuel ratio system or case study. Okay, but before we go through tuning using the Control Station software, let's go over some information about the tuning method. So the tuning method, essentially what it is the system is run in open loop mode. That means the controller is turned off, and we apply a step change to the controller. So for example, in this case, we're going to change the air-fuel ratio, and we just measure the open loop response. We're going to use the parameters, or we're going to fit the open loop response to a first order plus dead time model, and we're going to use those parameters to calculate the PID settings based on a specific process. And let's look at how we do those. So for the Conankun method, we'll use table 9.2 from Riggs Chemical and Bioprocess Control textbook, and the calculations are shown here. So once we measure, or once we apply the step change and we monitor the open loop response and model it as a first order plus dead time model, we will have the process gain, the time constant, and the dead time. We'll then use those values to calculate the P, the KC for a P-only controller, or the KC or the reset time for a PI controller, or KC, tau I, and tau D for a PID controller. Right? So remember, P-only controllers are selected for integrating processes. PI controllers are selected for fast processes, which is the majority of controllers for the chemical process industry. And PID controllers or PID modes are necessary when the dead time over the time constant is greater than about 1. All right, so essentially just once you have Kp, tau, and theta p, we just plug them into the equations and get the gain, time constant, or the gain, reset time, and derivative time. Now all of these parameters are based on models or based on correlations, and the calculations are achieved to get a about a quarter amplitude decay tuning ratio. So based on a typical first order plus dead time process, various models have been used and correlations have been made to do these types of calculations. So essentially we determine the parameters for a first order plus dead time model and just do a little bit of plug and chug. For the Conan Marlin method, it's a little bit more detailed than that method. Okay, so the following plots come from Riggs textbook, table 9 or figure 9.3.2, and that table shows correlation functions for either disturbance rejection or set point tracking. So these figures right here, figures A, B, and C, show the correlations to calculate Kc, which is shown on the left right here, to calculate tau I, which is shown on the left axis right here, and to calculate tau D. Okay, so these are correlations. So once we determine theta and tau, we can calculate things like fractional dead time. And then we use the fractional dead time to determine Kc times Kp, for example. And then once we know Kc times Kp, we can divide that value by Kp from the first order plus dead time model and determine Kc. And the same holds true for tau I and tau D. Okay, so let's go to the Control Station software and look at fitting the process to a first order plus dead time model. So this is how we do it in Control Station. I'm going to let this run for a second. Okay, and now I'm going to go over to File, Save Live Data to File, and I'm going to just call this Test 1. Just every 9th point is fine. Okay, so I'm going to let this run again for a couple seconds because it started over. Now I'm going to change the air-to-fuel ratio to 12. And now I watch the process respond. So you can see the process responds here. Now once it achieves a new steady state value, I'm going to go ahead and pause it by clicking this entry right here. I'm going to go File, Stop Saving Data to Live, or Stop Saving Data. Okay, and now I have data. So then I go to this Design tab. Under Design, I open up my Test 1 data. Okay, now with this data, I have to select the data that I'm going to use for the model. So the important things that we need to do is we need to have the manipulated variable correct and the process variable right. So the manipulated variable is the air-fuel ratio, and that's shown over here. So I'm going to move this value, manipulated variable, over here. And this is going to be necessary for the model. And then my process variable is shown over here. It started at 210 and it decreased. Okay, if you don't do this, your model is not going to work. Now, once I've done that, I can click OK, come back to the system, and I go Start Fitting. Voila. I have my model fit. So it shows here my data in white and then my fit over here in yellow. And then on the bottom of the screen here, I can see I have a gain of 12.37, a time constant of 8.64, and a dead time of 3.289. Okay, so first what I want to do is determine, okay, because my process reaches a new steady state, I'm going to use at least a PI controller. It's not an integrating process. If I look at my dead time to time constant, that's about 3.3 to 8.6, so it's less than 1/2. This means I want to use a PI controller. Okay, so now again, I'm going to record these values, 12.4, 8.6, 3.3. I'll probably carry a few more significant figures for the calculation. But now I have all the numbers I need to determine the parameters using the classical open loop tuning methods. So if I come back to my slide presentation, I can look here. So to calculate Kc in tau I, I'm going to use the second row. Okay, so to calculate Kc, I'm just going to plug those values, Kp, tau p, theta p, into this equation, and that's going to give me Kc, and I'm going to do the same for tau I. Okay, for this Conankun method, I'm just going to calculate Kc and tau I using these correlation plots. Okay, so you can see here that my theta over, which is was about 3, tau was about 8, so about 3 over 11 was my fractional dead time. It's going to be somewhere around here. I can divide this value by my gain, which was about 12, and that gives me my Kc for that process. Again, in this case right here, same fractional dead time, it's about 0.2, 0.3-ish, somewhere around here. Tau I over theta plus I. Right, this time now, theta plus tau is about 11. So tau I divided by 11 equals, about 0.6, 0.7. Right, now if I'm going to do this to determine my settings, I'm going to be a little bit more precise with my calculations, but for the purpose of this video, I want to demonstrate the process to determine these parameters. Okay, so this goes over, or this shows how to determine the PID settings for the open loop classical tuning methods. Again, just to reiterate, we turn the controller off, put the process in open loop mode. We apply a step change to our controller output, measure the response. We take the model and we fit it to a first order plus dead time model. We might be able to do that by hand using the equations from Riggs' textbook, or we can use that doing software as we did in this example. Okay, once we have those parameters, again, we can either just plug those into the equations to calculate our Kc and tau I, or we can use those along with the correlation functions to determine Kc, tau I, and tau d. Okay, so that about wraps it up. Good luck using this process to determine your PI or PID tuning methods for your process.